presentation today on data quality, and specifically we're going to be looking at applying some ideas and thoughts from manufacturing to how we can translate them to data. My name is Mike Robbins. I'm a big open source fan and a contributor as well, and I typically spend a lot of my time thinking about how folks can avoid spending so much time cleaning data, versioning data and enrichments, how that data gets processed, how we version it, as well as a bit on data quality automation and detection as well, which I'm going to be talking a little bit about today. My current role is CTO at Poplin Data, where we help a wide variety of companies with all sorts of data engineering problems and issues. So the story kind of really starts here. This is a photo from the 1940s of the Western Electric production line. This company was part of AT&T in the US. It was founded reasonably early, so late 1800s, by Elisha Gray and Enos Barton, and they had this very unique business model, and it basically meant that they sold a whole bunch of telecommunications devices, but they repaired the telephones and components that they sold onto various distributors at absolutely no cost to the customer. So irrespective of what broke, they never charged the customer for the repair. This kind of led to quite a unique position where they wanted to avoid and minimize as much as possible the costs involved in fixing these devices. So it drove them to really invest in what they call data quality and process control measures since really the 1920s, and particularly in the 1950s, where they started with this idea of SPC, or Statistical Process Control, all around optimizing the assembly line to minimize the number of quality mistakes and maximize visibility across the supply line and the production line. So what I'm going to kind of argue today, and the images on the left here are from the Statistical Quality Control Handbook. It was published in the 1956. It's open now, so anyone can read it. It's quite long, it's a few hundred pages. So we're only going to focus on a few screenshots today. So what I'm going to argue is today that a lot of the lessons from this handbook are really directly applicable, or can be applicable with a small amount of modification, to data pipelines themselves. So what were they trying to achieve within Western Electric? So fewer defects, fewer operators, less scrap material, so less waste, less product rejected by inspection, things like increased capacity, and just improving specifications and design. So if we look at those analogs with data pipelines, we can reasonably easily draw lines between those things, which is we want fewer low quality data points. We want fewer engineers to have to operate the system, less oversight in terms of human QA. We want less unusable data. This is a really core piece. Everything that we want to collect, ideally we want to be able to use. We also want to save time and increase throughput, and less data downtime as well. So particularly for service level objectives, we want to be able to uphold these as much as possible, as well as coming up with better specifications and designs for the data that we're actually collecting as well. So how did Western Electric, I suppose, go about doing this? We've got a slightly different pipeline here. We don't have a manufacturing pipeline. We've instead got something that's primarily collecting and processing data. So there's all sorts of different areas here where we can introduce errors and introduce low quality data. If we start at the collection process on the left, we can just simply miscalibrate our instruments. So they may not be collecting data in the way that we expect. This could be IoT devices, it could be browsers, it could be almost anything that you imagine that's responsible for emitting and collecting that data. You've then got processing and storage. So your processing procedures, there may be errors in the code there. It may need to reprocess data. Storage, depending on your level of redundancy here, you may see different corruption issues. You may not be storing things at the same level of precision that you want, seconds versus milliseconds versus nanoseconds. You've then got data modeling, feeding off that storage layer. So what is the business logic that goes and transforms this raw data into a consumable data model, whether it's a table or a view? Are those columns correctly typed? Is it usable data? And then finally, but often not finally, and obviously there's loopbacks between different parts of this pipeline, you've also got the analysis side of things, as well as machine learning models and algorithms. And something that you obviously need to be really cognizant of here is how different machine learning models can drift depending on what data they're being fed, as well as bias over time, which is increasingly becoming an issue that we're becoming more familiar with, I suppose. So in terms of the process capability studies of implementing this, I came up with 4 steps. So the first is to collect data from the process. The second is to plot those statistical patterns. The third is to interpret those patterns. And finally, the fourth one is a little bit self-evident, which is do what the patterns tell you. And this really suggests that the patterns are self-evident in terms of what needs to be done. So this is really a case of having a clear idea of what the pattern is and what the appropriate response should be for the pattern. And on the left-hand side, we've got the standard kind of scientific method, which is experiment, form a hypothesis, test that hypothesis, and finally iterate on that experiment as well to determine if you've got an improvement in what you're measuring. So the first step is really just collecting data from the process. So it's important at this stage to version almost every stage of the pipeline if you can. And this goes for collection, processing, storage, modeling. And really this is about enabling a contract between consumers and producers and having a really solid lineage throughout the pipeline so that you can tell what version of components have emitted certain events or certain data points, what version of data models have built a data model and processed data in a certain way. And this is really, really critical in terms of being able to debug this information down the line. So having versions of that stuff enables not just replayability through exactly the same versions of components, but also that debugging aspect as well. And next, really it's all about what emitted it, processed, transformed it. So if you've got atomic operations or batch operations, you really want to version them as much as possible as well. So one of the first things we can do is validate the data. And validating the data is a reasonably easy thing to do. And the example I've got here is specifically with JSON schemas. And JSON schemas are very useful because it's already an existing data validation framework. It can easily be applied to JSON or you can transform into JSON. And it allows you to reason about some reasonably simple things like what is the type of the field, what are the minimum values, maximum values, the formats of values. And one of the big advantages of using something like JSON schema and an already existing framework designed to do this is that it's available in basically every single programming language or environment you can think of. There's at least 20 supported programming languages, and if it's not there available in the environment that you're using, it's reasonably easy to write something in order to basically do so. So this is a nice example of how we can use JSON schemas. On the left-hand side, we've got our predefined schema for this NPS event. NPS should either be null or a number between 1 and 10 inclusive. And there's a timestamp field. The type is a string and the format is going to be a date time, so an ISO timestamp. And the only required field we have is actually the timestamp here. We can then take various different instances of our event. Our first event is going to valid NPS, valid timestamp. And our second event is going to fail because it doesn't have that valid timestamp. And at the bottom there, I've just put a small snippet of code to demonstrate just how easy it is to validate these events. But validating individual events is good, but what if we want to validate groups of events? We want to look at things like means or medians or potentially standard deviations over time. So validating not just individual data points, but collections and batches of data points is also really, really critical. So there's a few different ways of doing this. One is supervised tests. So one is to sit down as a human, figure out what the right values should be, means, medians, whatever they are, and write these tests by hand. The next one is kind of this semi-supervised idea of tests, which is you profile your data, you come up with some statistics, and you use those stats to enable the test that you're going to write. Maybe there's even some kind of automated test written for you. And then the final one is the least effort for the human side and the most effort on the machine side, which is entirely unsupervised tests. So you use ML to do this. There's really minimal to no curation here, and it's designed to look at your data set, again, extract those statistical properties and try and infer what you think those tests should be. So with this notion of profiling and bootstrapping these tests by using existing sample sets, we need to be cognizant that it's only ever going to pick up trends that already exist in the data. So you really need to make sure if you're going to go and do something like this, you've already got a trusted data set in place and you're able to use that data set as a ground truth. If it's already got anomalies in it or something like that, then these tests aren't necessarily going to encompass that and they may potentially skew what they end up writing for you. So one of the ways that we can profile is using something like Great Expectations. I've got an image here on the right of using the Capital One profiler, which is a Python profiler, and it can basically take just a standard pandas data frame, and then it's going to be able to calculate statistical properties for you then to go and bootstrap some of these tests. So it can do basic things. So categorical values is the one that I've got on the right here. The different frequency of values, minimums, maximums, depending on whether it's numeric or not, as well as some more advanced things. So towards the end there, you can see skewness of distribution and kurtosis as well. So you can test not just on kind of simple, basic descriptive metrics, but also things around distributions as well. And being able to profile this data set ahead of time is often much, much easier than writing these things from scratch. So now I'm going to jump into a quick demo of Great Expectations and use this open source Python framework to show you how you might generate some expectations for an example dataset. So the next step is really plotting it from here. And this is really going to be quite time dependent on what your measuring is. But typical things to plot here are things like service level objectives. So what is the deliverability of your data? What are the number of rows or batches failing validation versus passing validation? Is it a certain subset of data events? Is it from a certain application or is it from a certain source? And then trying to track down what those errors are and potentially what those errors mean as well. And that really gets into this interpretations part, which is what does a failure on a certain event or a batch mean? What information should we know about this failure? Is the message particularly descriptive? Sometimes they're not particularly descriptive because most systems aren't able to isolate these failures by themselves. They'll give you a general error, but it won't necessarily tell you why this failure is. On the right, I've got another image from the Handbook, which is what to do about freaks. So engineers frequently wonder whether they ought to throw away portions of the data that appear to be wild or to have been caused by a freak. In general, it is never wise to throw away any data in the calculations or plotting process. And this is a really important key idea when capturing points around data quality is just because you've got anomalies or things that fall outside of standard deviations, it's not an excuse not to capture these things. So as much as possible, try and preserve and version this data. Inevitably, it's going to be super useful down the line when you actually need to debug something or you need to plot this historical stuff over time. So where possible, you may not necessarily need to process it. You may quarantine it. It may not go into the data warehouse, but try and avoid throwing it out entirely. And then one of the next interpretations and thinkings that we need to do, which is what is the right corrective action when this sort of issue occurs? Is it to fix the process? Is there something upstream in the code base that we can fix that is producing bad data quality? Is it something in a Spark job or an ETL job that is just a logic error that is quite simple to fix? Is it the case that we potentially need to quarantine this data? So put it aside, reprocess it in some way, and then replay it through the pipeline. That's frequently the case. So that may be the case where you've got a timestamp, for example, and you need to trim the precision of it, or maybe you've got an incorrect type, something's been sent in as a string and you need to reprocess it as an integer. So typically where you're not losing information from the pipeline. Also, can you impute the data from another source? So if we've got two different timestamps, one's got millisecond precision and one's an epoch in seconds, are we able to impute that information from an additional field in there? This is sometimes possible, but not always possible, but quite often a useful shortcut if you've actually got that data somewhere else in the event. Finally, you've also got remove data. And by remove data here, I don't mean remove data entirely, but remove it from downstream processes. So it may get filtered out in your data model. It may get filtered out in a visualization or an algorithm. So the data is still going to be there in case it needs to be used for some reason or in case it needs to be analyzed, but you're going to remove it from downstream sources so that they're not impacted by this bad data quality. And finally, there's always the option of ignore, which is there may be nothing that you can do about it. You may want to include it in your final data set. So ignoring it as long as you're aware of what the issue is and the impacts of what those data quality issues are downstream, there's really no harm sometimes in very specific use cases of actually ignoring it and acknowledging that you're not going to do anything about this issue specifically. So I suppose what are the key takeaways from today? The first one is try and establish a lineage in your data pipeline. And this really acts as a contract between the elements producing data. These could be, again, browsers, IoT, smartphones, consumers. So these are your data models, visualizations, ML algorithms, all that sort of stuff, and really make it easy to trace everything through the pipeline. So if there's a component that goes wrong or starts producing incorrect data or unwieldy data, you've got an easy way of tying that back transparently to the component that seems to be an issue, and quite often it's a version of a component rather than necessarily the component entirely. You want to assert early and often. So do this as much as possible at the collection stage. Try and avoid it exclusively at the data warehouse stage, because by the time you get to the data warehouse, someone's going to have to be cleaning this data. So the earlier and more often you can assert the quality on not just individual data points, but also batches of data points, the better. Next one is invest in data testing tools and data quality tools. If you don't have these already, there's good commercial options. There's also plenty of fantastic open source options. I've talked about two, and I've got GitHub links on the next slide. Some of these are data profiling tools. Some of these are things like Great Expectations, which I've demoed in this talk. And a lot of these tools you can very easily integrate into CI/CD pipelines, so ETL processes as well. You can integrate as Airflow operators, for example, and you can also run these things on schedule. And finally, there's a few things I haven't had an opportunity to talk about in this talk, but missed but not forgotten here. So things like alarming and false positives, it's great to have data quality checks here, but unless there's alarms and unless they're going to the right people, it's very hard to do things about these alarms. And also false positives, you want to be reasonably conservative, because if you're raising too many of these alerts, they tend to just kind of blend into the background. Reprocessing data, so how we do that, how we think about data pipelines and data quality checks as a graph rather than necessarily a linear process. And also today, increasingly becoming more and more of an issue is privacy, which is the interlinking between data quality and privacy, which is, are you accidentally collecting personal data? How are you going to be able to detect an alarm whether you're collecting personal data, what the nature of it is, and whether it's necessarily intentional or not. So that's the end of my talk. Thank you very much. I appreciate your time. I've got my socials down there in the left-hand corner, my GitHub, as well as a few GitHub links to the projects I've talked about today. So Open Lineage, an open source product designed to determine the lineage between various different components of the data ecosystem. I've got the data profiler there from Capital One that's open source. Great Expectations, which is the testing framework we went through, and I mentioned a brief mention of DBT as well, a data build tool as a data modeling tool. So if you've got any questions, please let me know, and thanks again once for your time.